everybody. Good afternoon to everybody. May I audible? Is a screen visible to all of you?
Yes, sir.
Okay. Last time we have just discussed about a system calls. Let us will take a review of the this chapter once again. So in this chapter we are going to study different system calls such as open, read, write, shell seek, close, file creation, change directory and change root, change ownership and change mode, stat and fstat, dup, mounting and unmounting, link and unlink. These are the different system calls in this chapter we are going to study. Then syllabus is covered in the textbook as design of Unix operating system by MJ Batch by PHI publication and uh, CO4 for this chapter, that is implement all system calls related to the file system. So we'll study about the title of this chapter. The title is a system call, and a system call is a just what its name implies. It requests for operating system for to do something on the behalf of users program. The system calls are functions used in the kernel itself. To the programmer, the system call appears as a normal C function call. The central idea of this chapter, the central idea of this chapter is a system call provides a services of the operating system to the user programs via application program interface. That is, it provides interface between process and operating system that allow user level processes to request services of the operating system. System calls are only the entry point into the kernel system. Why this chapter is important in your syllabus? So in computing, a system call is a programmatic way in which a computer program requests a service from the kernel of the operating system it is executed on. The system call, it is a way for programs to interact with operating system. Remember the figure of the kernel or Unix operating system? At the core or central part is hardware, then a kernel, then different system calls, and then the user programs or other programs. So system calls which works as an interface between kernel and user or kernel and different programs. System call provides a services of the operating system to the user program via application program interface, that is API. It provides an interface between process and operating system which allow user level processes to request services of the operating system. System calls are the only entry point into the kernel. All programs need resources, must use the system calls. Why this chapter is included in your syllabus? That is different services provided by system calls. Which are the different services? The process creation and management, main memory management, file access, directory and file management, device handling such as input output devices, protection, networking. Then types of system calls. There are 5 different types of system calls such as process control, file management, device management, information maintenance, communication. These are the 5 different types of system calls. So out of them, process control, in process control, there are the system calls such as end, abort, create, terminate, allocate, then free memory. In case of file management, create, open, close, delete, read file, etc. These are the different system calls regarding the file management. So this chapter deals with the different types of system calls for the file system using different concepts explored, which are that concepts explored in previous chapters, such as in previous chapter, that is internal representation of file system. We have studied the, that is inode, how inodes allocates with ialloc and ifree algorithms, buffer allocations. In second chapter, we have studied buffer allocation, buffer release. So in this chapter, we deals with accessing of files such as open, read, write, lc, close. Then present system calls to create new files, create new node, that is with the help of system called mk node. Then suppose you should have to change your directory, then change root or change your owner, or there are for this change mode. For this you should have the use system calls such as a change directory chdir, then change root ch root, change own for changing ownership, change mode, that is change mode of read write execute, then stat fstat. For investigation of the system calls such as pipe, dup are important for implementation of pipe in the shell script. Mount, umount or unmount, these system calls are used in file system tree visible in the user. Then linking and unlinking change the structure of the file system with the help of link and unlink system call. Then present notation of the system calls as abstraction, which allows support different file systems as long as they confirm standard interfaces. And last section of this chapter will cover the file system maintenance. This chapter introduces 3 kernel data structures such as a file table with one entry allocated for every opened file in the system. Second, user file descriptor with one entry allocated for every file descriptor known to a process. And mount table, which contains the information for every active file system. In next slide, there is a figure, which in that figure there is a relationship of different system calls and different algorithms, that system calls or different algorithms related to with each other. See that figure carefully. See in this figure at the bottom, in second chapter we have studied buffer allocation algorithms such as get block, buffer release, buffer read ahead, and buffer write. In third chapter we have studied the different algorithms regarding inode regarding inode allocation in the file system, such as I get, I put. This combination of these two algorithm is named I algorithm. Then inode allocation, that is I alloc and I free algorithm. Then block allocation, alloc free and buffer map. These three algorithms we have studied in third chapter. Then in this chapter we are going to study a different system calls such as open, create, dump, pipe, close. These system calls are regarding with return file disk. Then open, create, change directory, change root, change ownership, change mode, stat, link, unlink, make node, mount, unmount. This system calls used for the algorithm use of name of I. Then for assigning nodes, the system calls are used as create, make node, link, unlink. Then in case of file attributes, the system calls as a change ownership, change mode, stat. In case of file input output devices such as read, write, lseek. Then in case of file system structure, mount and unmount. And for tree manipulation, change directory and change ownership. These are the different system calls with file system or file structure we are going to study in detail. So before that, we study introduction regarding the system call. What is the use of system call? System call that return the file descriptors for the use in another system call. System calls that use name my algorithm to pass a path name. System call that assign and free nodes using algorithms iloc and ifree. System calls that set or change the attributes of a file. System calls that do input output to and from a process using algorithm alloc free and buffer allocation algorithms. System calls that change structure of the file system. System calls that allow process to change its view of the file system tree. So first system call is open. The open system call is the first step a process must take to access the data in the file. The first system call is open. A process must take to access data in a file. The syntax of this open system call is fd is equal to open with parameters as path name, flag, and mode, where fd is a file description. That is, this data is stored in file description open with different parameters such as path name, flags, and mode. Path name, that is name of the file. Flag, which indicates whether file is open or not. And mode, there are different modes of the file system such as read mode, write mode, or execute mode. These modes gives the file permission if the file is being created. The open system call returns integer called as user file descriptor. Other operations such as reading, writing, else seeking, duplicating of the file descriptor, setting the file input output parameters, determining the file status, and closing the file, use of the file descriptor that open the system call. We'll see the example of this. Suppose, see in this file, see the structure of this file. If I right click on this file and go to the properties, see the contents regarding this file. This is the path name or name of the file. That is location of this file where it is stored. Then a size of that file, size on disk, when it is created, when it is created, when it is modified, when it is accessed. It have attributes or read only, or in case of advanced, or in case of security, it have file control access, modify access, read and execute, read, write. These are the different modes for this file. Then special permissions. Okay, so any file have different permissions such as read, write. When it was created, so for open system call in case of file system, syntax is syntax is d is equal to open path name, flag, modes. Path name indicates name of that file, flag which indicates whether file is open, and modes such as reading or writing modes in case of file is open. Then algorithm for opening a file. So algorithm open. Input for this algorithm is file name, type of open, then file permissions, then output of the file is file descriptor, that is FD. So convert the file name to inode with the help of the algorithm name I. If file does not exist, if you want to open some file and that file does not exist, then return error. If it is open, or if that file is exist, then allocate a file table entry for inode, initialize count and offset, allocate user file descriptor entry, set pointer to the file table entry. If type of open specifies tourniquet file, then free all file blocks with the help of free algorithms. Unlock file with the unlock file, that is inode locked with the name I algorithm, then return. Then output will be the FD, that is file descriptor. This is algorithm for opening a file. So kernel searches the file system for the file name parameter using algorithm name I. It checks the permissions for opening the file. After it finds the incore inode, allocates an entry in the file table for the open file. The file table entry contains a pointer to the inode of the open file and a field that indicates the byte offset in the file where the kernel expects the next read or write to begin. Kernel initialize the offset to 0 during the open, that is it starts from starting point to the end point, copying the all contents of that file during the open file, meaning that initial read or write starts from the beginning of file by default. Alternatively, a process can open a file in a write append mode, in which case kernel initializes the offset to the size of that file. Kernel allocates an entry in a private table in the process of user area called as user file descriptor table and notes the index of that entry. Index in the file descriptor that is returned to the user. The entry in the user table points to the every global file table. Then a data structure after open the file. See in this figure, there are three types of open. FD1, file descriptor 1, open the file, etc. password for a read only, and group is other, O for other, RD for a read only. Open this file, etc. password, so which is stored at suppose third location of user file descriptor table. See in this figure. Then in file table count is 1 because it is open for a read only. Then FD2, open file local other group for a read and a write, so which is stored at user file descriptor table at location 4. Here also count 1 because here open read and write. Then fd3 file description 3 open, etc password file once again open, etc password file once again. Initially it is opened for a read only, now it is opened for a write only. So initially at third location for a read only count is 1. Then at fifth location here also count 1 because it is opened a write only. But same file is opened, etc password, same file is opened two times. First for reading purpose, second for writing purpose. In inode that is index of that file is same. It is opened two times, so here count is 2 for etc password file. And local file here only one times it is opened, so here count is 1. See the figure carefully. So this figure shows the relation between inode table, file table, and user file descriptor table, that is in data structure. Each open returns file descriptor to a process, corresponding entry to the user table in the unique entry kernel through only one. See here inode, etc password file is opened two times, but in user table entry is two times at third location and fifth location. But at inode level there is entry only once. The file table entries all instances of an open file point to one entry in core inode table. The kernel notes that the capability to read or write in the file in the table entry allocated during open call. Suppose these two operations such as fd1 is equal to open, etc password, other group for read only, and fd2 open, private file other group for read only. So see in this figure, these two processes, there are process A and process B. Process A has opened etc password, first opened is etc password file for reading purpose, so here count is equal to 1. Then process, again process 1 has opened a file for writing, same file is opened, that is etc password is opened by process A for writing. For writing here count is equal to 1. And by process B has opened etc password file for reading purpose, so here count is equal to 1. But there are three counts, two counts by process A. This is count 1 for reading, this is count 2 for writing, and this is count 1 by process A has opened for reading etc. password file. So total counts are 3. Did you get? See the figure carefully. Here, same file, etc. password has opened by two processes, process A and process B. By process A, it has opened two times for reading purpose and for writing purpose. And by process A, it has opened for reading purpose. So total count is 3. Then next, this figure shows the relationship between the appropriate data structures while both processes have the file open. Again, each file call results in allocation of the unique entry in the user file descriptor table and the kernel file table, but the kernel contains at most one entry per file in the in-core node table. The user file descriptor table entry could conceivably contain the file offset for the position of next input output operation and point directly to the in-core inode entry for file, eliminating the need for a separate kernel file table. This example shows one-to-one relationship between user file descriptor entries and kernel table entries. The first three file descriptor tables, such as a 0, 1, and 2, are called as a standard input, a standard output, and standard error. These three file descriptor tables are standard input for 0th location, standard output for first location, and standard error for a second location. The processes on Unix system conventionally use a standard input descriptor for a reading purpose or input the data, standard output descriptor for a writing purpose, that is output of that file, and standard error descriptor to write error data or message regarding that file. Then next, a system call is a read. The syntax for read is number is equal to read, fd, buffer, and count. So whatever the total count or total number, it is the output of that file. Whenever a system call read that particular contents of that file, you should know the parameters for reading that file as file descriptor, then buffer, and total count. So fd is file descriptor returned by the open, buffer, which is address of the data structure in the user process that will contain read the data on successful completion of the call, and count. Count is the number of bytes the user want to read and the number which is number of bytes actually read. So kernel gets the table entry that corresponds to the user file descriptor with the following pointer. See, this is the algorithm for reading a file. Algorithm read input file descriptor address of the buffer in the process number of bytes to read input user file descriptor address of the buffer in the process buffer of number of bytes to read the output that is count of bytes copied from the user space. So algorithm get byte get file table entry from user file descriptor check accessibility of that file whether file is accessible or not. If it is accessible, then set parameters user area from user address byte count, then input output to the user, get inode from the file table and log that inode, set byte offset in user area from the file table offset. While count is not satisfied, if count is not satisfied, then convert file offset to the disk block using algorithm buffer map. Calculate offset into the block number of bytes to read. If number of bytes to read is 0, that is end of file, then stop or break of that loop. If there are number of bytes not equal to 0, that is more than 0, then read that block with buffer read ahead algorithm. If buffer read ahead is not working, then with the help of bread buffer read algorithm, you should have to read the contents of that block, copy data from system buffer to user address, update user area fields to the byte offset, read the count, address to the right into the user space, release buffer, then release buffer with the help of B release algorithm, then locked which is locked in buffer read algorithm. If this while loop is execute, if this count is not satisfied, if count is satisfied, then unlock inode, update the file table, offset for next read, then return total number of bytes to read. This is algorithm for reading a file. See this algorithm carefully. So we have seen the algorithm for reading a file. So there are sets several sets of input output parameters in user area as shown in this table. See the table below of this slide. There are five input output parameters such as mode, which indicates a read or write, reading or writing mode. Then count of bytes for reading or writing. Then offset, byte offset in a file. Then address, target address to copy data in user or kernel memory. Then flag, which indicates if address is in user or kernel memory. Specifically, it sets the input output mode to indicate a read is being done for mode. Then flag, which indicates input output will go to the user address space. A count field indicates number of bytes to read, the target address of the user data buffer, and finally an offset field to indicate byte offset in the file where the input output should begin. After the kernel sets the input output parameters in the user area, it follows the pointer from the file table entry to the inode, locking the inode before it reads a file. The algorithm now goes into a loop until the read is satisfied. The kernel converts the file byte offset into a block number using the algorithm buffer map, and it notes the byte offset into the block where the input output should begin and how many bytes in the block it should read. After reading a block into a buffer, it is possibly using block read ahead algorithm. It copies the data from the block to the target address into the user process. It updates the input output parameters in the user area according to the number of bytes it read, incrementing the file byte offset and the address in the user process where the next data should be delivered, and decrementing the count of bytes it needs to read to satisfy the user read request. If the user request is not satisfied, the kernel repeats the entire cycle, converting a file byte offset to a block number, reading the block from the disk to a system buffer, copying data from buffer to the user process, releasing buffer, and updating the input output parameters in the user area. If the cycle completes either when a kernel completely satisfies the user request or when the file contains no more data, or if the kernel encounters an error in reading the data from disk or copying data to the user space. So completion of cycle or for reading data stops, there are four conditions. First, if all data is has been read, or there is no more data, or kernel counters an error in reading the file to the disk or copying data in the user space. The kernel updates offset in the file table according to number of bytes it actually read. The kernel updates the file table data entry according to the number of bytes actually read. That is, a successive reads of a file deliver in file data in a sequence. This is a sample program for reading a file. Here, integer file descriptor, character, little buffer with size 20, then big buffer with size 1024, then file description, that is open etc file for a read only by other group, then a read with parameters such as fd, then buffer and 20. So read fd big buffer and with file size 1024, then read fd little buffer with size 20. This is a simple program for reading a file. So the open returns file descriptor that user assigns a variable fd and uses in the subsequent read calls. In the read a system call, kernel verifies that the file descriptor parameter is legal and that process had done previously for opening a file, that is for a reading. In this program, it stores the value of liter buffer 20 and stores the values of little buffer 20 and 0 in the user area corresponding to the address of user buffer, the byte count and the starting byte offset in the file. It calculates the byte offset from 0, that is 0th block of the file, and retrieves entry for the 0th block in the inode. In this buffer, there are two types of buffer, little buffer and big buffer. So assuming that block exists, a kernel reads the entire block of size 1024 bytes into the buffer, but copies only 20 bytes from the user address little buffer. So it increments the user area byte offset to 20 and decrements the count of the data to read to 0. Since the read has been satisfied, the kernel sets the file table offset to the 20 so that subsequent reads on the file descriptor will begin next time file reading of file starts from the 20, and the system call returns the number of bytes actually read at 20. For second recall, the kernel again verifies that file descriptor is legal. Okay. that a process had opened file reading because there is no way of knowing that user read request for the same file that was determined by legal during the last read. It stores in user area the user address a big buffer to the number of bytes the process want to read, that is 1024, and starting offset from the in the file from 20 taken from the file table. So it converts the file offset to the correct disk block and read that block. If the time left between read calls is read calls is small, there are some chances good that the block will be in buffer cache, but the kernel cannot satisfy the read request entirely from the buffer because only 1004 out of 1024 bytes for these requests are in the buffer because 20 are already copied. So it copies last 1004 bytes from the buffer into the user data structure big buffer and updates the parameter in user area to indicate that the next iteration of the read loop starts at byte 1024 in the file, that the data should be copied to byte position from 1004 in the big buffer, and the number of bytes to satisfy the read request is at 20. This is the explanation of the reading file program. Now we move towards a next system call, that is a write. Up to this we have seen only two system calls: open a file and reading a file. From in next lecture we will study next system calls. Okay, if you have any query, then ask.